Hello guys, how are you? Hope that you are doing good and you are all fine. In our video here, we're gonna to continue talking about nuclear reactions, and today we will start with section 4, which is talking about nuclear fission and nuclear fusion. In this section, we have to know the difference between nuclear fission and nuclear fusion, and know the key terms as we see here, which is nuclear fission, chain reaction, critical mass, nuclear reactor, nuclear power plant, shielding, control rod, moderator, and nuclear fusion. We will start with nuclear fission, which is a very heavy nucleus split into more stable nuclei of intermediate mass, which means here we are splitting a heavy atom to lighter atoms. And actually this process releases a huge amount of energy, and it could be spontaneously or artificially by bombarded the atom by neutrons or particles. For example, when uranium-235 is bombarded with slow neutrons, a uranium nucleus can capture one of the neutrons, making it very unstable. So after capturing the neutron, the atom will be, or the nuclide will be unstable. Then it will be split into medium mass nuclei with the emission of more neutrons. The mass of the product is less than the mass of the reactants, and the missing mass will be converted to energy, which will be released out. And sometimes this atom, after being bombarded with the neutrons, it will be splitted, as we see here, uranium-235 split to krypton and barium. Then another neutrons released to bombard again another uranium atoms. And those atoms are split to different other atoms, and so on. Now, this is what we mean by chain reaction, which is the reaction in which the material that starts the reaction is also one of the products that can start another reaction, as you can see here. So here we have starting with uranium, and in the second line here we have another neutrons, which bombard another quantity of uranium, and so on. The reaction will continue until all of the quantity of uranium atom is finished. So it will be like a chain. Now, this chain reaction will continue until, as we said before, the whole quantity of uranium-235 is finished, or when the quantity of uranium-235 is less than needed. So a lot of neutrons will be escaping without hitting uranium. We call this mass, or this amount, critical mass. So the critical mass is the minimum amount of a nuclide that provides the number of neutrons needed to sustain a chain reaction. Uncontrolled chain reaction give the explosive energy to atomic mass. While in nuclear reactors, actually, we use a controlled fission chain reaction to produce energy and radioactive nuclides. So, if the reaction is uncontrolled, it will give us a huge amount of energy. This is why we need to control the reaction in our labs, or to produce electricity, like what actually happened in the nuclear power plants, which is using of energy as heat from nuclear reactors to produce electrical energy. And in this nuclear plants, we have 5 main components, which are shielding, fuel, control rods, moderators, and coolant. The shielding is radiation absorbing material that is used to decrease exposure of radiation, especially gamma rays from a nuclear reactor. So, at the first, we need materials that will absorb the huge amount of radiation, especially gamma rays, as we said before, because it has the maximum penetrating ability. So we need to absorb it and prevent it from going outside. So we must use those materials as shielding for the gamma rays. Now, uranium-235 is typically used as the fissile fuel to produce energy as heat, which absorbed by coolant. And we're going to talk about coolant later. Now, the second component is control rods, which are neutrons absorbing rods that help control the reaction by limiting the number of free neutrons. If we go back here to this shape, as we can see, at each step we will have neutrons escaping from the other arrows, and those neutrons are going to hit another amount or another atom of uranium. So if we control the number of neutrons released, we can control the number of uranium atoms that will be bombarded, so we can control the chain. Here you have to know that we have two types. First, if we control the number of neutrons or the speed of neutrons. So if we decrease the speed of neutrons, that means that the neutrons will not be able to bombard another atom. So also, this is how we can control the chain reaction. And here we use the moderator, which is used to slow down the fast neutrons produced by fission. As you can see here in this shape, we have the nuclear reactor here where the reaction happens. We will have a huge amount of energy. This energy will be moved to water, which is steam generator. The steam will goes on this path to steam turbine generator. This generator will provide us with electricity, and we will have electricity from the other side. Now, the steam will be condensed again in this container here. It will be condensed to water again, and this water will be pumped to the first vessel again in a circular motion. And this is how we could have electricity by using nuclear power. As you can see here we have the control rods with the fuel and moderator and coolant, which is liquid water under high pressure inside the reactant to absorb heat released from the reaction, to increase the temperature of water and convert it to steam in the steam vessel. Now, the other type of our nuclear reactions here is the nuclear fusion. As you can see here, fusion of hydrogen nuclei into more stable helium nuclei provides the energy of our sun and other stars. In a nuclear fusion, low mass nuclei combine to form heavier and more stable nucleus. In this type of reactions, amount of energy released is much more than the nuclear fission. In our sun and stars, for example, as we said, hydrogen nuclei combine at extremely high temperature and pressure to form helium nucleus with a loss of mass and releases of energy. In fusion reactions, we could use the energy if we were able to control the fusion reaction. Now, scientists are studying ways to contain the reacting plasma that is required for fusion.
And plasma is an extremely hot mixture
of positive nuclei and electrons, and there is no known material that can withstand the initial temperature, which is about 10 to the power 8 Kelvin, required to induce fusion. Scientists use strong magnetic field to suspend the charged plasma inside a container, but away from the walls. Additionally, a large amount of energy is needed to initiate fusion reactor. For fusion to be a practical energy source, more energy needs to be generated by the reaction that is put into the reaction. So, to initiate the fusion reaction, we could use a fission reaction to start it. That's all for now, and by this lesson, we reach the end of our chapter. See you later in our next chapter, which is organic chemistry. Thank you and be safe.